Hello?
Hey, how are you?
Oh, I'm doing fantastic. Thanks for asking. How's your day coming along?
Doing pretty good, pretty good.
Glad to hear it. So, do you have any questions from our last class at all?
No.
Fantastic. So, we've been spending a great deal of time just reviewing all of our integration rules because we're going to be getting to a section where we not only identify situations where we have to use particular rules, but we're going to be focusing an entire section on applying integrals to solve real problems. Things like volume and physics problems and things like that. But we want to make sure we have the foundations down solid before we move on to the later material. So I feel like you're pretty good on review of you're pretty strong in that area. So I thought to kind of bridge the gap between U sub and the trig substitution, like we've been doing earlier, I want to give you an integral that kind of focuses on both of those. So suppose you have this.
Okay.
Let's say we're trying to integrate the cotangent of x. What kind of a strategy do we use in a situation like this one? Or what? There might be more than one.
Well, the first thing you do is you look at the rule. I mean, you have to think about what you have. This is pretty much like all of a mental process. This one is relatively simple. You have cotangent of x, and since we're integrating it, it means that cotangent of x is the derivative of something else, and which is I know by the rule that it's the derivative of sine. So in this case, it would just come out to sine x plus c.
You're really close. If it were cosine of x, then yeah. But what we have here,
Oh, cosine. Oh, I saw cosine. Sorry, not.
no problem. It's been
um.
a long day. I can sympathize with you for that one. So what we have is cotangent of x. It's a bit different. It's a bit more complicated, but nothing we don't know how to handle. What kind of a strategy do we want to use here?
Well, first thing that comes to mind is we could rewrite it, but I'm not entirely sure if that would help us.
It's always worth a try. So can you think of, just off the top of your head, what way do you think of right away to rewrite cotangent?
Cosine x over sine x.
Sorry, could you repeat that, please?
Yeah, cosine x over sine x.
Fantastic. Do you want to write it?
Yeah.
Why is it better to have cosine over sine instead of just cotangent?
Um, it gives us more to work with. There's
Exactly.
other things that are equal to sine x and cosine x, so we might be able to rewrite it even further.
Perfect. It gives us many, many more opportunities to use special techniques we've learned in this class. All right. So is there any more simplification we have to do, or are we ready to just dive into the calculus part of this right away?
Um, I think we're ready to dive into the calculus.
Oh, I agree. Perfect. So what calculus tools can we use in a situation like this one?
Well, I think USA would work in this one.
Oh, I agree. You want to set it up for us?
Yeah.
Have at it. So remember what happened when we had something like this in the last problem? We kind of first thought we could make this into u to the 0 power if we apply that power rule. We found out that that's actually not the right thing to do. What do we want to do instead of the integration power rule in this situation?
Um, No, yeah, no, this is actually, and it's just natural log
Mhm.
when you have a.
Yep, perfect. du over u turns into natural log of u. Fantastic. So we're going to be spending some time reviewing those trig rules. We're going to be dealing with integrals that require a bit of trigonometric simplification. We're going to be using those identities quite a bit. So let's say we have a single term, a single factor, cosine, this time it would be cubed of x. Can you think of any strategies we can use to rewrite this before we integrate? And
Um,
by the way, if you don't have like a trig identity sheet pulled up right now, I suggest you pull one up on your phone or maybe see if you have one laying around somewhere because we're going to be needing that for these problems.
I have one. I have one pulled up.
Fantastic. Came prepared.
This one I would say we could write it as cosine squared x and then cosine x.
Beautiful.
Um,
You're absolutely right. But why is that beneficial?
well, I know cosine x, no, cosine squared x is equal to another, it has its own has its own identity. Um, it's like one of three, but then it also just gives us more opportunities to manipulate it.
So if we have something like this, let's say we have sine to some power, and then we just have a single power of cosine. This is it's really nice to have it in this form because a could be anything. It could be sine squared x, sine cubed x, sine to the 100,000 x. And the reason it works out really nicely is because it doesn't matter what a could be. Sine is always going to be sine is always going to be u, and then the cosine is always going to be du. And then the same thing
Hmm.
goes if we have the other way around. What if we have a single power of sine of x, and we have an a power of cosine of x? That means u is going to be cosine in this case, and then du would be sine. So we always want to have a single power of this and then some other power of cosine, or we want a single power of cosine and then some other value of sine, because that sets us up to do a u sub. So our goal is to set this up in a similar way. Ultimately, we want to have a single power of sine and then a different power of cosine, or a single power of cosine and then some other power of sine. So can you think of a way to kind of set it up like this, where we have a single power of just one of those, either sine or cosine?
Yes, I
So
can, but I had a question. If, for example, if we had cosine a x, cosine to the a power x, and then just sine x, how would du be just sine? Because if isn't the derivative of cosine negative sine? Do you move that negative to the other side when you calculate du over dx?
absolutely. You would end up with a situation like this one. You would move the dx to the other side and the negative. Good question. You would end up.
And then the negative in a question, and then in the question, the negative would just go outside of the. Oh, okay, yeah, that makes
Exactly.
sense. All right.
So do you want to take a shot at this one?
Yep.
Fantastic. Looks great.
Hmm.
So this one is definitely a u sub situation. The question though,
Yeah,
do we want u to be sine or do we want u to be cosine in this situation?
I think I
Well,
think
if you
in
look
this case we're gonna want it to be sine
exactly, we always want u to be the thing
the
that has a
one.
power that's not one. So in this case,
Yeah,
yeah, it would be sine.
but how would you calculate du over dx
You just
sine?
well, actually, we wouldn't have a u be sine squared. We would just have it be sine, just sine
Oh, and then u
first.
squared, u squared.
Exactly, you got it, u squared.
Yeah.
It works really nice because you could have any number there. It could be sine to the seventh or sine to the 10th. It doesn't matter what power we have as long as we have a single power of cosine. U2, that's a pretty good band. Have you heard
Yeah,
of
I know
it?
about them. Yeah. I think my iPhone or my mom's iPhone came with like a free album from them,
Yep,
and
I
that's
like
how I
the
heard
band.
about them.
I like the band. I did not like that album, and I liked it even less when I found out it was forced on me. I tried to delete it,
Yeah.
I just couldn't delete it for some reason.
Oh, you can't delete it? Huh.
I deleted it, but it came back.
Oh,
It's like some horror movie. It just keeps coming back no matter how many
yeah.
times you click delete. So real quick, how do we evaluate the antiderivative of, let's pretend
Oh,
it's just x squared? How would we evaluate
I
antiderivative?
I derived. It's gonna be you add one to the exponent and then divide the whole thing by that result.
Perfect.
And then
Yeah,
I forgot to expand u. Oh my gosh. We said
fantastic. Very nice. Let's try something a little bit different. Let's try something that's kind of along the same lines as this, but different enough to warrant some different strategies we might have to use.
mhm.
So let's say we have an odd power of sine. Let's just make it sine to the 5th power of x. And then we have an even power of cosine. Let's just make it squared. Can you think of any strategies we can use to help us with this one? Any identities that might be useful in this situation?
Um, yes, I think so.
Give it a shot.
Um, all right. Could you move it to the left?
Oh yeah, sorry. And
Oh, that's okay.
I can even shrink it a little bit. There we go. Yeah, looks good so far. So how'd you know right away that this is the approach we want to use here?
Um, well, I remember doing this kind of problem, and usually what you want to do is you want to take the one that has the odd exponent because the all the identities they pretty much have even exponents, or if they do. So I'm thinking my first thought was to just find a way to maybe u sub sine x or cosine squared x or something like that, and also use an identity before doing that though to simplify it a little further.
Perfect. Continue. Okay, we're doing great so far, but is there a way we could maybe simplify that middle part? Is there a way we could maybe simplify this even further?
Um, maybe by making it 1 minus cosine squared x, that quantity squared, but I'm not sure if that'd help.
Oh, I think it would. It would definitely help because then we can apply the binomial theorem. We'll just have three distinct terms, and then things are really easy to work with after we reach that point. That
Okay.
way, this whole middle part right here would only contain cosine. No, yeah, it would only contain cosine terms and no sine terms, making things a little bit easier for us. And then you can FOIL it out, or you can use the binomial theorem, whichever you prefer.
Oh, well.
Hang on a quick second. So
Hmm.
we're going to have to expand this first before we can multiply the sine through it.
Oh, we have to. Okay.
So
Oh,
you,
yeah, that's true. Forgot about the exponent there.
so you can either FOIL it out, or you can use the binomial theorem. So if we do the binomial theorem, it would just be, oh, you got it.
Yeah. Uh,
Didn't mean to steal your thunder there.
No, I was just thinking about how it would work in this case because I know the one with the a and b, a minus b squared, that formula.
So now we can break it up into three different integrals. So we want to not only multiply the sine by everything in the parentheses, but also this cosine squared. So make sure you
Okay.
multiply all three of the things by sine and cosine squared. So this is one of those many instances in calculus where we have to make things uglier and nastier before we can make them nicer. So what kind of a strategy do
Yeah,
you want to use here? What kind of a strategy would be good in this situation?
I think U sub is gonna apply for all three of them
I
at
agree.
least.
So what should we have be u and what should we have be du?
For the first integral, I think u is gonna have to be cosine x.
Yep, exactly.
Um,
You're right. So the nice thing about that kind of a setup is we can have the same u for all of them. So u is going to be the cosine for the first one and the second one and the third. So
yeah,
we can have
and
the
this,
same u and u for all three.
okay.
Fantastic. Very nice. So you seem to be
Yeah, that
doing
wasn't
pretty.
so bad.
Yeah, exactly. You seem to be doing pretty well with this. I know it's tedious and it's a lot of work, but you have a really good understanding of how to set the problem up and how to execute it. So very nicely done.
Honestly, today I feel like I'm starting to like see how I need to do, or I'm starting to see through the problems and like see past them and see how I need to set them up and whatnot.
You're reaching that point much faster than I did when I was a student. So that's always nice.
Yeah, but I mean, you have that. You know how it was when you were a student, so you know how to teach it probably a little more effectively.
Yeah, not to mention this is my fifth time teaching calculus, so I have a little bit of experience.
Ah,
Yeah,
yeah, that might be the thing. That might do the trick.
I've tutored calc for I think maybe 8 or 9 years, but this is my fifth time actually teaching the class myself, so it's always fun. So let's say we have something like this. We're going to change things up with a definite integral. Um, how do I want to do this? Let's make this like that. So I want to see if you can just identify right away what kind of an identity would help us with this one. So far we've been using the Pythagorean identities quite a bit. Do you think that's kind of like what we want to do here? Do we want to use another Pythagorean?
I think so. But I'm not entirely sure. I don't think it would
So
help
if we do, we would turn that into 1 minus cosine squared x. Would that help us at all?
I mean, looking at that, we could break it up into two integrals, but that second integral, I'm not sure it would. I think we'd have to do the same thing, and it'd be one of those loops again. But at the same time, there was one question where we had like one of those loops, and at one point we had gotten what we had on the other side of the equal sign. So we
Exactly.
moved it over and solved it that way. So that might help us out because I can see us getting back to sine squared x by doing that also, that Pythagorean identity.
So you're thinking of recursive integration by parts. So it works really well recursively if we have kind of like what you described, a loop situation. So in that situation, it works really well if we have, I'm going to put a black box there because I'm too lazy to write what should be there. So it works really well if we have something like this. I'm going to get rid of the limits of integration for now. They're not necessary. Or actually, here, if this was minus, if we had minus sine squared x instead of plus. So it works really well if only we have different signs on opposite sides of the equal sign. So for example, on the left side we have plus, on the right side we have a minus. It works really well because we can add this integral to both sides.
Yeah.
This part goes away and we just have 2 times whatever integral this is. But let me ask you a question now. What happens if it's plus on both sides? Does it still work?
I'm not too sure because I mean you pretty much get rid of the entire integral, and
And then,
we're trying to find something that's equal to the integral. So
I mean, it's one way of making our,
and then yeah, so you're left with 0. I'm sorry.
exactly. Yeah, exactly. It makes our problems disappear, but not in the way we're hoping. It
Yeah.
literally disappears. So for some instances of integration by parts, it works really well. But in this case, it's going to end up being the same sign. It'll make the whole thing disappear. So it wouldn't really work in this case. So we don't want to use the Pythagorean identity. There's actually a different identity.
We're gonna get a plus.
So yeah, if we keep
We
writing,
we would get a plus in this case.
yep, if we do the loop, if we keep looping through the Pythagorean identity, we would have a plus on both sides, and that wouldn't work.
Uh-huh. Okay.
So see if you can think of any other trig identities that would be useful in this situation.
Um, I have an idea.
All right, let's hear it.
All right, actually, where'd that go? I was looking at I was looking at this sheet I have for trig identities. It's the one you sent me, but now just give me 1 second. I'm thinking like we could try to turn it into a double angle, and then it might be easier to, but I'm not sure if that's
You're
what I'll
exactly
do.
right. It is the double.
Otherwise, I can't really see any. formulas or identities that might help us.
So you're absolutely right. We do want to
So
use
from
the
sines. Oh, I don't know if you can hear me, but I did hear you say that.
Oh, can you hear me now?
Yeah, yeah.
All right, cool. I just wasn't sure. I just wanted to make sure you got the message somehow.
Yeah, no, I heard that, but then I think I spoke over you and then none of us understood each other.
You're fine.
I'm just I'm not entirely sure. I was thinking by like changing sine squared into something else and then using it to get something from a double angle formula and then using that to, but
You're absolutely right. We do want to rewrite sine squared using a double angle formula. So give it a try. You're exactly right about the strategy. All right. So which of these would make the most sense in our situation?
um I think the top one is more simple, but as far as which one, I'm not sure because I forgot what you would do with that cosine 2x, and we have it in both of them, so it's not really gonna matter. Uh,
Well, if we
I mean, it will matter, of course, but like as for right now, I'm sorry. Go ahead.
so if we try this one right here, this one wouldn't really work all that well because we still have cosine squared x. We would take the integral, and then we wouldn't be back where we started. We'd do the Pythagorean identity, turn that into 1 minus sine squared, and then we'd be back where we started. So this one actually wouldn't really help us all that much. We want to use this one right here. This is the one that will help us the most.
Mm-hmm.
So go ahead
Okay.
and rewrite the integral using this identity, and then it will become a little bit more clear why this is the right one to use.
Oh, wait.
All right, looking good so far.
And I'm pretty sure our next move is to just split this up.
Mhm.
I do have a question. The 1/2 would go to both integrals if we were to split it up, right?
Yes, indeed. Make sure they both get the differential.
Oh, yeah. No, it's sorry.
So where did that 1/2 x squared come from?
Oh, which one?
Where did this right here come
When you integrate, I'm pretty sure. You add so we had 1,
from?
and then I'm pretty sure that just comes from x. So 1 is the derivative of something else. So if we had x, we need something x to a power that when you subtract 1 from that power gives you 1. And oh yeah, I see that's not gonna work.
Yeah, if we take the derivative of this, we just get x, we don't get 1.
Oh, it's just x. I think I was overthinking there.
And then what do we do with cosine of 2x?
I think I'm thinking U sub, but I'm also thinking there was one rule for, oh gosh, I'm pretty sure it was for integration where you had to do it for every step. It was like chain rule. No, so that was for derivative. I'm thinking the opposite of the chain rule, but I don't remember what that was. Uh
Something with an inner function and an outer function. What do we want to do
yeah,
with the inner?
yeah. I'm sorry.
What do we want to do with the inner function? It's something we've been doing quite a bit so far today in the first 20 minutes or so.
Um
The integral equivalent for the chain rule would be u substitution. This is a u sub.
oh, you so I mean we set 2x equal to u possibly.
Yeah.
I'm not sure. I'm looking at it, but I don't know if u sub's gonna work here. Or if it does, we don't use it the way we normally do. I think that's what it is here.
So if u is 2x, then what's du?
Uh, um, two. Oh, well, yeah, 2 dx, and then
Oh,
we can just make that du over 2.
yep, exactly.
Okay. Oh, sorry.
You're fine. No worries. And this is where we need that unit circle. So I'll draw that for us off to the side.
Actually, I think I'll be fine without it.
Alrighty.
Or I mean, I just want to try from memory.
Good call. That's very admirable.
Okay. Three degrees, right?
Sorry.
3 pi over 2 is 270 degrees, right?
That's correct.
I believe.
Yes.
Okay. And so sine.
Fantastic. Don't worry about simplifying.
No?
No, I mean, this is perfectly fine.
Okay.
Nice job. I know it was,
Whew.
but you stuck it out and you did great.
No, these are I feel like I'm getting a little better.
Oh,
Still
you did.
gotta
Yeah.
practice a lot more, but I feel like, I'm it's like you said, we're just trying to achieve that point where you do so many that you know immediately what to do. And I feel like I'm approaching that point
Oh,
the more
you're very, very, very close to that point. I can tell. Like I said, this is my fifth time teaching calculus. I can tell when students are really, really close and you're almost there.
well, that's good.
So you know what? In those periods where you're staring at the problem, wondering what to do, your brain actually grows a lot more than you do during the actual problem solving. So when I'm sitting there scratching my head, wondering what to do, those moments are much more impactful than the work itself. So
Yeah, yeah.
let's try something else.
Give me 1 minute. I'll be right back in like less than a minute.
No problem. Take your time.
Hey, so sorry about that.
No problem. You're fine. So what do we want to do here? We have an even power of tangent and an even power of secant. This is a lot different than the ones we've been dealing with so far. So take your time, just kind of digest it. Think about what you might want to use here, what kind of a strategy you might be able to apply. Think in terms of calculus and think in terms of pre-calculus too.
Well, first thing that comes to mind is secant and its derivative, as well as just tangent and its derivative.
Yeah. That's a good place to start. I always like
Doing this.
Sorry.
No, you're good. You're good. I was ending there.
I was just saying that I like to think about those derivative relationships because we know integrals are the opposites of the derivative. So for example, we know that the derivative of tangent of x is secant squared of x. So
Yes.
you want to think about a way of approaching this so that we can apply those derivative and integral rules. We also know that the derivative of secant is secant of x times tangent of x.
Well, I think here, first thing that jumps out is u sub, and using u sub since we have secant and tan, and there's just two derivatives of the trig functions that involve these. So I think what this problem is going to be about is finding out which of those derivatives we can use more to our advantage. And looking at this, I'm not sure. Is if you try to like create uh the secant squared or the secant x and tan x, you still have these leftovers that you have to get rid of somehow. So
there is a way of dealing with leftovers. Do you want to give that a try and then
yeah,
think of a way to deal with the leftovers?
yeah. So for now, I guess I will. I think in this case, our secant squared x is just gonna work better. So
Yeah, I agree. Mainly just because of this right here.
yeah, so we're gonna want to set it up to where tan becomes our u, and or is that right? Tan to be our u.
So it's kind of like the relationship with sine and cosine. Remember we had, well, that's the wrong word. Remember we had something like this where sine could be any power, but we have to have cosine be a single power. Or conversely, we could have cosine be any power, but sine would have to be a first power. The same relationship applies in this problem, except instead the secant has to be squared instead of a single power. So ultimately, we want this where capital A could be anything under the sun. So how do we go from this to that is the question.
Well, before that, just so I understand, our goal here is to make this U subable pretty much. So in order to do that, which one do we want to be our U? Is it because when you take the integral, it goes back to the original, meaning what U has to be is the derivative. So in this case, secant squared x is there. So we want secant squared x to be the U, right? At the end
We want that to
when
be,
we're done manipulating.
we want that to be the derivative.
Oh.
We want to
Oh,
be
okay. Yeah. So that would equal.
So how do we deal with having that 2 on the outside? So we can't have a du squared. We have to do something with this 2. Can you think of a way to get rid of that?
Oh, I was still. Maybe you just make it secant 4x. I think that's
Well, we had that before. Actually, we want to do something a little bit different than this.
oh. Secant x squared. I think secant squared x has its own identity. It's equal to tan squared x plus 1. So I think we want to just have one secant squared x and then a tan squared x plus 1 and then a
Exactly.
tan 6x dx. And then
Beautiful. So
what we have now is a lot of work.
hang on a second. One thing we could do is distribute this through, but there's actually another way we can do this. I want to show you the other way we could approach this. So right off the bat, what would be u and what would be du?
Tan x would be u and du would be secant squared x.
Perfect. So du is here and there. So what we have in parentheses, this is u squared plus 1. Well, that didn't look neat. U squared plus 1. And then we have u to the second power. And then du. It saves us
Yeah.
a lot of writing, saves us a lot of work to do with it.
Wow. I was originally thinking foiling with secant squared x and tan to the 6x and then separating it into two different integrals. Would that have worked or would but just taken a lot longer or would it have not worked?
I recommend you try it. Now that you know this method exists, I want you to try the other.
Okay. So okay. Um and then here we set up our u, all that. That's gonna be u 0, 2. Oh my gosh. Whoa, what just happened?
What?
I don't know. So something just erased somehow. U is equal to just what
Now it's
the
coming back. What? I don't know what's going on. Like what you wrote erased, and now it's coming back.
yeah, me neither. I don't know. Regardless, I know what I wrote anyways. I'll just leave it like that. So then we have a du here, and we have u to the 8 plus secant squared du there, and then u to the 6th. I'm gonna go out on a limb here and say that it is gonna work, but I'll go through with it just because. So
Yeah,
we're
please do.
gonna end up with tan to the 9x over 9 plus tan to the 7x plus c. Uh, did you still have that copied?
Well, something happened here. This isn't quite right, but we don't have enough time to address it. So what we're going to do is we're going to tackle this one once again when we meet. So are you available tomorrow?
I should be, yes.
All right. So what do you
I
think?
don't think I won't be.
All right.
I'm sorry?
What about 6:30 tomorrow again? Is that okay? Okay.
Yeah, that's fine. And if you'd like a little earlier as well tomorrow, maybe just let me know. Because tomorrow I should be free the whole day. So if you wanted to, if there was another time more convenient for you, just let me know.
Perfect. Sounds great. You have a wonderful evening, and I'll see you tomorrow.